We're going to continue our discussion of rotating kind of things and torques by introducing a new idea, which is center of gravity. And to see why we need that idea, let's think about the torque caused on something by gravity. Here is my wrench, and if I have this right here, then this wrench is free to pivot about this point right here, right? So we've got this pivot right here, right? A clear pivot point. And if I let go of this, then gravity will cause the wrench to rotate clockwise. Okay. Behold, gravitational torque is causing the wrench to rotate clockwise. Okay. Well, what if we wanted to calculate how much torque gravity is exerting on this wrench, right? Clearly there is some torque in the clockwise sense. What if we wanted to calculate how much? So here's our definition of torque, right? It's R times F times sine of phi. And what is R? It's not necessarily the radius of the round thing in the problem. It is the arrow. It points from the pivot to where the force is applied. F, that's the force, of course, and phi is the angle between R and F. Okay, so looking back at this, there is some torque causing this thing to rotate in a clockwise sense. What's causing that torque? Well, it's definitely gravity. What would be my R and my F and my sine of phi? Well, the force is the weight, right? So we have the weight. The weight is acting on this here wrench, right? Where? Where should we, because where should we put this acting, right? Because R is the distance from the pivot, right here, to where the force is applied. So where should we say this weight is applied? Is it all applied out here at the end? Well, no, because that's overcounting the radius for some little chunk of mass over here, right? I think the thing to recognize is that every little centimeter of this wrench has a different radius, right? Every centimeter has some force of weight acting down on it, but every centimeter has a different radius. Which radius do I use? Well, that's the idea of the center of gravity. Right? Where do we put this? We should put this arrow at the center of gravity. The center of gravity is this model that's a simplification model. It allows us to take a very complicated situation and reduce it to a much simpler situation with equivalent results. This gymnast is certainly going to rotate like this. In this case, this gymnast is going to rotate in a counterclockwise sense. And so here we see definitely a torque caused by gravity in the counterclockwise sense. But notice that every little pound of her body is at a different radius, right? So the force on this part of her body is at a different radius than the force on this part of her body. So what R should we use? Because it's different for every single molecule, really, in her body. Well, what we do is we assume that all of the weight is at this point called the center of gravity. And sort of our standard symbol for it is shown in that picture. It's this little, almost looks like a BMW symbol or something. That is the symbol that we use to identify the center of gravity. And that's a pretty standard symbol, not just our textbook. So that's the idea of center of gravity. And so we can think about it in terms of torque, and that's totally valid. We can get there in almost a more straightforward way, right? The center of gravity is the point where I can put my finger under that point, and the object will balance. So here we see a uniform object. This is just a copper pipe, and it's uniform, right? It's even. Where do we expect the center of gravity of this object to be? Well, hopefully in the center, right? It should balance in the center. So the center of gravity is this point also, where if I put my finger under the center of gravity, the object will balance. And so there I found it pretty close. Oh, pretty close. Okay, so the center of gravity of a uniform object is right in the center. Makes sense. What about a non-uniform object? What if this was our object? Where is the center of gravity of this object? Here, I'll give you some choices. Where is the center of gravity of this hammer? Is it A, right on this end, B, right in the middle, C, closer to the hammer head, or D, right on this end? What do you think? Well, hopefully you chose C. C is the correct answer. How do we know that? Well, It's the point at which the hammer will balance, right? And so where does the hammer balance? It's somewhere in there. Right about there. Oh, right? So, indeed, C is the best choice. Behold. Okay. So, for a oddly shaped object, it may not be in the center. For a uniform object, the center of gravity is always in the middle. Where is the center of gravity for this L-shaped piece? I don't know. What do you think about it? Well, this is kind of a weird one to think about, right? But the center of gravity does not have to be in the object. Here, the center of gravity is definitely closest to A. To see why that might be, well, I have a shape like that. This is my framing square. And so, this is a little trickier. Here, this is almost like a one-dimensional object, right? And so, by finding where it balanced just along the line here, then we could find where the center of gravity was, in this direction, right? But here, we've kind of got two directions. So let's see. If I hang it like this, it balances right there, right? Kind of right underneath this hole here. And if I hang it the other way like this, then where does it balance? Oh, somewhere in there, right about there. Right about there. So, in other words, the center of gravity then is directly below this point. It's at the intersection of this line here and this line here. Where is that? Oh, somewhere right about right here. Right now, notice these two sides are not equally width, so it's right about here. So again, not within the actual object itself. And we'll find that with odd-shaped objects, right? Where is the center of gravity of this ball? Right in the middle, right? Assuming it's uniform, which it's a baseball, it probably should be. In other lectures, it is an electrical charge. We're not there yet. Okay, so where is the center of gravity of this ball? Well, it's in the very center of it. Yeah, that makes sense. Where is the center of gravity of this roll of tape? Well, certainly not not on one side, right? The center of gravity of this roll of tape is right here in the middle where there's no tape and no cardboard and no nothing, right? So the center of gravity of this roll of tape is right in the geometric center because it's uniform, but guess what? There's no tape in the geometric center. And indeed, I can use some tape to add a little structure to this. And where do I need to put my finger to make this thing balance? Well, right in the middle. So indeed, it does balance on a point right in the middle where there's no tape at all. Okay, so that's sort of a conceptual introduction to what the center of gravity means. How do I calculate the center of gravity? If you've got an object physically in front of you, you could use your finger and figure out where it balances. But what if I give you a math problem and you have to calculate it? Well, if you've had calculus, you've actually done these problems and had to do some calculus to do it, and we're going to simplify things, right? So we're only going to ask you to find the center of gravity for discrete objects where the center of gravity is obvious. Here's what I mean by that. We're going to, if we have a collection of objects at different coordinates, then we can find the center of gravity of that collection of objects. And just to kind of tell you, before we go through all of the steps here, where that might apply, a situation like this, right? We've got 3 balls here connected by massless rods. Where is the center of gravity of this object, right? That's how we could use this strategy here that I'm introducing to find this, and we will in just a second. So what are we going to do? First, you need to choose an origin for your coordinate system. You can choose any convenient point as your origin. So, for example, if you were trying to find the center of gravity for this and doing this math here, right, then, a common point might be to pick this as the origin, right? Now, that's fine. Maybe your friend picked this as the origin. Will you get different answers? Well, your numbers will be different, but you should agree on the point, right? You'll both agree. Your math will both tell you that the center of gravity is right here. But if you picked this point for your origin and your friend picked this point for the origin, then that will have slightly different numbers associated with this point, simply because different origins. Okay, so you have to pick an origin, and that's an important step to actually decide where will that be. In some problems, it'll be obvious. In other problems, it won't be. But you need to decide. And there's no, and I guess the other point I wanted to make, there's no wrong choice, right? It's just a matter of picking your origin, doing your math, and then interpreting your answer at the end according to the origin you picked. There's no wrong choice of origin. Okay, And then you want to determine the coordinates of the different particles for the different masses, right? So we need to determine the coordinates for all of the different masses. And then we run this equation. And so in order to find the x center of gravity, it's x1 m1 times plus x2 m2 plus x3 m3, all over the sum of the masses. The y position is y1 m1, y2 m2, y3 m3, over the sum of the masses. Let's just try using this strategy to find the center of gravity of this collection of 3 balls. They are connected by massless rods. So we're supposed to find the x and the y positions of the center of gravity. To start with, let's just draw this on our piece of paper. Okay, so there is our situation. We've got 1 meter here and 1 meter here. So that's our situation. Our first step in our problem-solving strategy is to pick an origin. Well, I can see a few different points here that would be acceptable and reasonable. Maybe we could pick here, here, or here. Those would all be perfectly good choices for our origin. I don't know. To me, right here seems like the obvious choice. Let's pick right here as my origin. That gives me a coordinate system x and y. Our next step is to list out the coordinates of each of our 3 points. This one right here is at x equals 0, y equals 1 meter. This one's at the origin. That's at 0, 0. And this one right here is at x equals 1 meter, y equals 0. Great. Our next step is to apply the equation. So we have the equation that the x center of gravity is. So here's our equation, right? And notice, if I gave you a problem with 10 things instead of 3, then you just have 10 terms on top and 10 masses on the bottom. I won't give you 10 things, but if I did, you could solve that problem too. So now we just go ahead and we plug in our numbers. x1, oh, that's 0. m1 is 1 kilogram. x2 is also 0, also 1 kilogram. And x3 is 1 meter times 2 kilograms. All over the sum of the masses. That's 1 kilogram plus 1 kilogram plus 2 kilograms. And so you see my kilograms cancel, and I end up with 2 over 4, 1/2 meters. That is my x center of gravity. Okay, so our x value was 0.5 meters. Let's make a little room, and then we'll do the y value. So here is my equation for the y center of gravity, and we can just plug in our numbers, can't we? And so here we've plugged in all our numbers, and we see that we get y center of gravity equals 1 over 4, that's 1/4, or 0.25 meters. Okay, so now we have an x and a y. Our x center of gravity was at 0.5, so that's right here. And our y center of gravity was at 1/4, so it's right here. Right, so there is my center of gravity. My drawing's looking a little cluttered here. Let's make a little room. Okay, so there we go. That is where my center of gravity is. Now let's talk a little bit more about this coordinate system business, right? We picked this as a coordinate system, as our 0, right? And we did our math, and we got 0.25 for the y value and 0.5 for the x value. Let's say your friend did this problem, and they chose, say, this point right here as their origin. Do they get the problem wrong? No, they don't. They get the problem right also. They also agree that the center of gravity is right here. But when they do their math, their y value is the same. They still get y. Their y value is the same, right? They still get y equals 0.25. But their x value is different. What they get for x, they get negative 0.5 instead of 0.5. That's okay. They picked a different origin, so they should get a different x value. But we both agree that the center of gravity is right here. So you do have to be a little bit careful when you're doing, mastering physics problems. They'll tell you where the origin needs to be, because that's the only way it can know whether your answer is right or not, is if it knows what origin you're using.